In this video, we're going to talk about the relative rate of change of a function. I think the best way to understand this is to look at a couple examples. So first of all, suppose you're trying to decide which stock to invest in. We have two options here. Stock A is growing at a rate of $2 per year, and stock B is growing at a rate of $1 per year. You might think, well, this is obvious, right? Stock A is going to be a better investment. It's growing faster than stock B, but not so fast, right? What really matters is not just how much it's growing per year, how many dollars per year it's growing, but also what is the current stock price. So if stock A is priced at $100, well, then growing at a rate of $2 per year, that's only a 2% growth rate. In fact, if you take 2 divided by 100, you get 0.02, which is really 2%. That's a 2% growth rate. That doesn't really seem that fast. That's not necessarily that great of an investment. Now, stock B is growing at a rate of $1 per year, but what if the current stock price is, let's say, $4? Well, growing at a rate of $1 per year, that's a 25% growth rate, right? 1 divided by 4 is 0.25, or in other words, 25%. Notice that stock B would be a much better investment. So, what really matters here is not the absolute rate of change of the stock price for these two stocks, $2 per year or $1 per year, but what's called the relative rate of change of the stock price. So this one would have a relative rate of change of 0.02, or expressed as a percentage, it'd be 2%. This one, the relative rate of change is 0.25. Now, I'll give a precise definition of relative rate of change in just a minute, but we're just trying to understand the concept for right now. Let's look at another example. The population of a country is growing at a rate of 1 million people per year. Now, is this population growing quickly, right? Is this explosive growth? Well, doesn't it depend on what the original population is, right? If the original population is, say, only 10 million people, well, then growing by a million people per year, well, that's a 10% growth rate. That's pretty quick. I'd say that's explosive growth. On the other hand, if the population is 25 million and it grows at a rate of 1 million per year, well, 1 divided by 25, that's 0.04. That will be a 4% growth rate. Now, that's still pretty fast growth, but not nearly as fast as 10% growth. Now, if the country really huge, so like China or India or something where they have a population over a billion people, well, growing by a million people per year would actually be a very slow growth rate. It'd be less than like 1/10 of 1% per year. So, again, what matters is not the absolute rate of change of the population, which would be a million per year, but the relative rate of change of the population, which takes the million and divides it by the current population. Okay, so what's the relative rate of change of a function? Well, remember that the rate of change of a function f is really f prime of x, right? The derivative represents a rate of change. The relative rate of change of a function is the derivative divided by the original function. It's f prime of x divided by f of x. That's the relative rate of change of a function. So in the previous example of population, the derivative would be like a million people. It's increasing at a rate of a million per year. But the bottom function f, that would be the original population. Or when it came to stock prices, the one that was worth $100, the 100 would be in the denominator. That would be the current stock price. The derivative would be like the 2. It's increasing at a rate of $2 per year. And we take that 2 divided by 100, that's 0.02. So our definition says the relative rate of change of a function is defined as f prime of x divided by f of x. Now, the percentage rate of change of a function is really just the same thing, only we multiply it by 100. So a lot of times our relative rate of change will be something like 0.073. And so if we take that number and multiply it by 100, we're going to get 7.3 or 7.3%. And that's the percentage rate of change of the function. So let's do an example. Let f of x be 12,000 minus 7x squared. Find the relative rate of change of f. And in part B, find the relative rate of change of f when x is 35. Okay, and round your answer to 3 decimal places. And then last of all, find the percentage rate of change of f when x is 35. Okay, so let's do part A. What is the relative rate of change of f? I guess we can write RROC. Relative rate of change is going to be f prime of x divided by f of x. Now, what is f prime of x? Well, the derivative of 12,000 is 0. The derivative of this is minus 14x. Okay, there's our f prime of x divided by the original function, 12,000 minus 7x squared. Now, there might be ways to simplify this. And if you're looking at an answer in MyMathLab, sometimes it simplifies. It might divide out certain numbers from the top and the bottom. But it's okay to leave it unsimplified. So MyMathLab will even mark it correct if you don't simplify your answer. So that's the relative rate of change of our function. And notice this itself is a function. Now, what is the relative rate of change of your function at x equals 35, or when x equals 35? Well, what we need to do, and I guess for our notation for this, we'll put f prime of x over f of x, and we'll say evaluated at 35, or at x equals 35. And so what we're going to do is just take this and plug in 35. So we have minus 14 times 35 over 12,000 minus 7 times 35 squared. Okay, when you work this out on a calculator, you get negative 490 over 3,425. And make sure in the denominator that you do the order of operations correctly. You square the 35 first, then multiply by the 7, then subtract that all from 12,000. And when you work this out in a calculator, you get this is approximately negative 0.1430659 dot dot dot, or rounded to 3 decimal places, this is negative 0.143. That's the relative rate of change of the function when x is 35. Now, what is the percentage rate of change? Well, we just take this number and multiply it by 100. So that's pretty easy. The percentage rate of change is going to be negative 14.3%. That's the percentage rate of change of the function. So again, to find the relative rate of change of a function, you just take the derivative of the function and divide it by the original function, and you'll have a formula here that involves x. If you want to find the relative rate of change of f at a particular number, or when x is a particular number, you now just plug in that number for x, and then you write it out as a decimal. Okay, I guess you could leave it like this, but I think MyMathLab a lot of times asks you to write it out as a decimal and maybe round it to, say, 3 decimal places. And then the percentage rate of change, you just multiply this by 100. So essentially move the decimal over 2 places. Now, in the next video, when we talk about elasticity of demand, we're going to see the importance of relative rate of change in a real-world example. Now, one last thing, sometimes the relative rate of change is written a little bit differently. You could actually think of the relative rate of change of a function as the derivative with respect to x of natural log of f of x. In fact, what's the derivative of the natural log of a function? Well, remember, the derivative of natural log of something is just 1 over the something, but then times the derivative of the something, right? That's by the chain rule. Remember, the derivative of natural log of x is 1 over x. Derivative of natural log of f of x is 1 over f of x times f prime of x. But notice this is just f prime of x over f of x. Okay, so you could use this as your definition of relative rate of change of f as the derivative of natural log of f of x. But I think it's just easiest to remember it like this. It's the rate of change divided by the original function. Okay, it's f prime of x divided by f of x. So you don't really need to know this about a natural log. The only reason I bring this up is if MyMathLab, in its explanations of how to do the problems in this, like, help me solve this, it may end up using natural log like this. But you can find the relative rate of change without worrying about this natural log here.